All right, so we're starting with a little bit of factoring practice, bringing us back to this, just kind of continuing to keep this idea fresh in our minds. When we're factoring, the very first thing we do is we look at each of our terms that are involved, and we look to see if there's anything I can divide out of all three of them in this case. So first, looking at the numbers, the 3, 21, and 36. Can I divide them all by the same thing? Yep, I can divide them all by 3. So I'm going to pull 3 out. But you'll notice there's also x's in every term. So how many x's can I pull out of every term? 3. Yep. Because that's the fewest number of x's in any of the terms, right there. And so that's what I'm going to factor out. It's the 3x cubed. So I'm going to do the 3 divided by 3, which is 1, and then x to the 5th divided by x cubed. Remember, that means you subtract the exponents. And so that's going to leave me with x squared. So it starts as 1x squared, and then we just clean it up into x squared. All right, then the minus stays a minus. 21 divided by 3 is 7. X to the 4th divided by x cubed is x to the power of 1, but of course we don't have to write the 1 there, so just 7x. Then the plus stays a plus. 36 divided by 3 is 12, and then x cubed divided by x cubed is 1. Notice it's not 1x. It's not x to the 1. It's just 1, which means there's no x left in that, and 12 times 1 is just 12, so it's just a 12 there. There's no more x left behind on that last term. All right, then the question is it completely factored at this point? And you'll notice that this is a quadratic inside of our parentheses here. So it's possible that we can take it a little bit further. It's possible that we're going to end up with 3x squared and then 2 sets of parentheses because it's a quadratic. Now, how do we know if it can go further? Are there 2 numbers that add to negative 7 but also multiply to 12? Yes. Yes, there is. So then it is factorable. So our answer will look like this. Those 2 numbers that add to negative 7 and multiply to 12 are negative 4 and positive 3. Oops, sorry. Not positive 3, negative 3. There we go. And so then this is our final answer. That's what we're working toward. Now, a little side note here. If you wrote the x minus 3 first and then the x minus 4, that's perfectly fine. You can do that. But a little bit of a side note here, a side question. What if I wrote my answer for some reason like this? Is that okay? Well, kind of. What if I was just wanting to write x, but I wrote x to the power of 1? Is that okay? Kind of in the same way. That still means x, right? But it's just not good form. You know, we're being a little bit sloppy. The same thing is true about this one here. Putting that in the middle, it's technically correct. It technically does mean the same thing. But it's not very good form. We always like to write that monomial term first. Partly because if we're a little bit sloppy in how we write this, what's that 3 mean? Does this 3 mean to the power of 3, or does it mean 3 times the x cubed? It can be a little bit hard to tell. So that's why we tend to put those out front here instead. So although it means the same thing, it's not the way we want to write it. And that will start coming up more later with other stuff we do as well. But I just want to kind of put it on your radar, make sure you're aware. So then this is what we're going to be working with for solving our systems. Please write down this system, and then I'm going to be working this one through for you up here, and you'll be able to take notes on how this process works. All right, now as we take a look at this, first of all, what's different about this from what stuff we were doing like last week? Well, you'll notice that every single one of these equations includes every variable as well. This one, we don't have one of the equations starting with just one variable, or even just one of the equations starting with 2 variables. They both, all 3 of them actually have all 3 variables. So this is getting more like a true 3 by 3 system, where it's got everything going on in it. But our basic idea behind it and our basic process is the same. We're going to be trying to take my big old 3 by 3 at the start, and I'm just going to try to shrink it down into a 2 by 2. And then I'll be able to solve my 2 by 2 system the same way that I was solving stuff before. So, when you write it out, definitely work on lining it up. If you line up all your x's, y's, z's, and numbers and all that stuff as you write it, writing super neatly, it's going to help to avoid errors. As you're going to see, if you make one error right off the top, it's an even bigger pain, right? And we've already seen that it's a pain when we make some of those mistakes. So you definitely want to be very, very careful as you're doing this to help avoid having to redo them. And so our strategy then, in order to turn my 3x3 up here into a 2x2, is that I'm going to be looking to figure out the easiest variable that I can eliminate twice. I don't just need to be able to eliminate it once, but I need to eliminate it twice. Now this one is set up to where we should be able to look at it and see that fairly quickly. Which variable would be a good one to eliminate here? Yeah, the z's. The z's are set up beautifully to eliminate, because you'll notice that this negative 10z at the first, I can add that to this 10z, or I can add that to this 10z. And both of those are going to cause me to be able to eliminate the z. So that's going to work out nicely. So that's my strategy going into it. So the first thing I'm going to do is I'm going to take those first two equations, and I'm going to write those first two as their own little system of equations. Yes, include the curly brackets next to it. If you start leaving that out, your work is going to be a bit harder to follow. And you'll notice that as I rewrote them, that's all I did, was I just straight up rewrote them. I didn't do anything else to them yet. If you try doing a couple things at once, you're more likely to run into errors. All right, now in this case, remember I chose these two equations here because those 10z's, they're already set up to add to 0, and that's what I want to do. And so because of that, I now am going to go ahead and just add those two equations together. And so I'm just going to add straight down on my x's, my y's, actually think about the z's to make sure they add to 0, and our number. And when we do that, in this case, we end up with negative 5x plus 7y equals a negative 22. And so notice what we just found. We just ended up with an equation here that has just x and y in it. We eliminated the z out of it. If I had two of those, I'd have a 2x2 system that I could solve. And so that's my goal next, is to find another equation without the z in it that I can combine with the one that I just made. So the very first thing we did, remember, is I combined the first equation with the second in order to make the z's cancel out. I'm still going to make the z's cancel out. Which two equations should I combine in this case? Well, that first one combines nicely with, the third. And so I'm next going to combine the first and third equation. And so just like before, I'm going to write those as their own equations. And so I'm combining the first and third equations there. And then, just like before, once you've written them out as a system, include the curly bracket, go ahead and add those two equations together. And so that addition gives us negative 6x plus 10y equals negative 28. So notice what that's done for me. I now have two equations, each involving the same two variables. And yes, the variables must be the same, otherwise it doesn't help us at all. So now that we have that, I can take those two equations of two variables and turn that into a 2x2 system. And so that was our whole goal. By eliminating the z twice, I ended up with two equations with two variables, a 2x2 system. And now that I have a 2x2 system, I solve it using all those techniques we've been using all along. So go ahead and solve it out from there. And when I started working it through, I decided I was going to make the x's eliminate. That was my personal choice. So I multiplied the first equation by 6 and the second equation by negative 5. Again, you have other choices you could have made as well, but if you're wanting to match up with what I did, that's what I'm doing. And so, after multiplying, I then end up with a system of equations where the x's will cancel out. So I add them straight down, solve for y. Once I know what y is, I then can plug it back in. Now when I'm plugging the y in, I have a couple choices. I want to plug it into one of the equations that has just y and one other variable. So it's one of those two that I used in my 2x2. I chose to plug it into the first one. Again, personal choice. You could have plugged it into the second one. You would still get the same value for x. All right, and then to find z, we do the same thing that we've been doing on all of our other 3x3s. I take the two variables that I know, and I plug them in for those two variables in one of the three variable equations. And again, it doesn't matter which one you do. I chose to plug it into the first one, as you can see here, but you also could have plugged it into the second equation or the third equation, and you'd end up with the exact same answer, which is that z is 1. That means that this problem is done. This is our solution up here. X is 3, y is -1, and z is 1. All right, so we've gotten this one written down. And again, try to line it all up as neat as you can. It helps to avoid possible errors cropping up. And of course, that's a big deal with these, because one little mistake early on can be compounded later, and it can be a pain to find. All right, so our strategy. We still want to start the same way we started the last one. I'm going to try to find the easiest variable that I can eliminate twice. So we're going to do two separate combinations trying to eliminate the same variable. Now in this case, which ones does it look like it's going to be easiest to eliminate twice? Now if I'm having to do it twice, yeah, it looks like the y's, because all three of those, it could be a fairly easy elimination. But something cool, some of you have already been seeing it, something cool can happen with this, right? I want to grab the first and the third equations here and line those up. So go ahead and write those out, and we'll see what it is that's kind of cool that happens in this particular case. Now in this particular case though, some of you are saying, well, but the z's cancel out. Yes, they do. And in fact, when we add these together, that's going to work out really conveniently for us. Because when I add these first and third equations together, both the y and the z ended up canceling out on us. So I was just left with a single equation with the x in it. I had 8x equals -40. Now, that's certainly not common. This is not a typical thing to happen, but it certainly is convenient because we already know one of our values. We now know that x equals -5. All right, now having found out what x is, what's that mean that I do from there? Well, you actually have a couple options. One option that I'm not going to show up here, but you could do if you wanted to, is you could actually take the x equals -5, and you could plug that in for x up here. And then having done that, you could then create some 2x2 systems out of that. So you can do that. But I'm not going to show you that way because there's multiple ways to do it. And I want to show you continuing kind of with the idea of what we've been doing today, where I'm going to choose two different equations to add, but I'm still going to try to eliminate the same variable. Now, remember the first time I was trying to eliminate the y. It just happened that the z's also eliminated. And that first time I did that by combining the first and the third. So this time I know that I have to use the second because I haven't used it yet, and you're going to have to use all three of them. And so which one would be easiest to combine to make the y's cancel out? Should it be the first or the third with that? Yep, looks like the third. So I'm going to combine the second and the third equations, and so I write those out as their own little system of two equations. And then go ahead and add the two equations, and we end up with this, which, remember, our goal was to end up with two different equations that did not have y in them. And we've done that. It's just they don't look quite as similar to each other as they did in the last one. In this case, I got this equation I just found, and the other equation was just the x equals -5. But I can still combine those, right? Because I can take that x equals -5 and use a little bit of substitution here. I can just plug that in for the x now. And because this equation only has the two variables in it, when I plug in the x, it'll only have one and I can solve it. Once you found z, that means just the y left. I take my x, I take my z, and I plug them back into any of the original equations. I chose the first, and then that gets us our last value. And so we got our solution then. X equals -5, y equals -1, z equals 4, and we're done because we found all three values.